And ladies and gentlemen, welcome once again to the Simpkins Physics Corner, Week 3 asynchronous lesson for AP Physics. It's graphing time. So let's get into it without further ado. This is my buddy, the Moving Man, compliments of FET, Colorado, great physics website, lots of good resources. Let's go ahead and tune this guy up here to do some motion. All right, what is the motion of this guy going to look like if he starts at a position of -10? I'll give him a velocity of 3 and an acceleration of 0. Let's watch him. Now you see he's moving across the screen at a constant speed. Now the interesting thing here is when I do that and we chart that on a graph, we're going to look at what these graphs look like. Now before we start, let's consider what they might look like. If I'm going in a constant speed, then what would my position time graph look like? Well, let's go back to our slides here. Wouldn't my position time graph look like a steady straight line going up? I know it's not the straightest, but I'm working with the stylus. Give me a break, all right? Because you're covering the same amount of distance per time interval, the slope would be steady. We mentioned that the speed is the slope the other day. A position time graph of a constant velocity should look like a line that has a constant slope. But the velocity should be steady because we are not accelerating. And what does a steady thing look like? Well, let's say the velocity is 6. Well, then a second, oh, sorry about that. Then a second later, it would still be 6. And a second later, it would still be 6, and still be 6, and still be 6. And what shape would I get if I connected all those points? I would get a horizontal line. So here's the first distinction we can make. A position time graph for a constant velocity object will have a line that looks either like this for positive slope moving forward, or like this moving backwards. And of course, if you're at rest, your slope would be 0, so your speed would be 0. So that's what your position time graph might look like. But the velocity time graphs for a constant velocity object are just going to be a bunch of horizontal lines. Let's take a look at what this might play out to look like. So let's set them up again. We got the initial position of -10. We'll give them a velocity of +4 and no acceleration. Let's see if this is what we expected. Well, we expected this guy, since he's going at a constant speed, to have a position time graph that looks like a straight line with a positive slope since he's moving forward. And if we look at the velocity time graph, boy, this thing is lagging so hard. Oh, maybe it's because it's recording? I don't know. And you can see that the velocity graph is a horizontal line indicating a constant speed. It's not changing. Down here, you notice the acceleration is just tracking at 0 because there's no acceleration. So boy, is that dogging it. But let's go ahead and reset all of our settings for the moving man. What would it look like if he's going backwards? Let's try this one out. Let's see if the velocity is -5. Remember, velocity is a vector, which means it has direction and magnitude. Oh, yeah. And you see here the position time graph has a negative constant slope. Can anybody guess what the slope, the numerical value for slope might be of the position time graph? If you said -5, you would be correct. Why? Because the velocity tells us the slope of the position time graph, or rather the slope of the position time graph tells us the velocity. So if you look right here, the velocity is negative and constant. We know that because the position time graph is a straight downward trending line. And the velocity here is that constant -5 value. And you notice once he hits the wall, it just kind of jumps up to 0 velocity. So this is just a short introduction into what happens when you are moving and what happens when you graph motion. What gets really interesting is when you cause things to accelerate. So let's go ahead and take a look at this. What if my initial velocity here is 0? And what if I accelerate? Acceleration. Now, acceleration is a change in velocity. So we expect that our velocity would start at a value of 0, but then that velocity would increase as we go. And so here's the cool thing. You see the acceleration is a pretty boring horizontal line. They always will be in our class because we don't deal with non-uniform acceleration. We always have uniform acceleration in Physics 1. But you'll see that the acceleration graph here is tracking steadily, not at 0, but at +1. I don't know why they picked such a large scale. There it is. You can see that the acceleration graph is just a horizontal flat line. Why? Because it's a constant acceleration. The velocity is increasing. Why? Because the acceleration is causing the velocity to change. And here's where the really cool part comes in. The position time graph is a curve. Now, why might that be? Well, I'm going to get into this here in just a second. But just suffice it to say for now that a curvy position time graph indicates acceleration. I'm going to close this page because it's really lagging me out hard here. And let's take a look at a summary of all this information. You might need to pause, and I'll provide some printouts of this. But this is everything you need to know about position time graphs and what they mean about an object's motion. Let's walk through it here. A horizontal line shows no movement. Why is that? Well, look, if my position is 0.2 at 0 seconds, and then at 1 second, my position is still 0.2. What did I not do? I didn't change my position, which means I didn't move. All right, so that's why a line with a slope of 0 on a position time graph indicates no movement. Remember, slope is the speed, right? If the slope is 0, you're not moving anywhere. If you have a positive slope on a position time graph, that would indicate that you're moving forwards, because we say slope is the speed because they both start with S, but really slope is the velocity, because velocity has magnitude and direction. So the direction part of this would be positive. It would show that our velocity is going forwards if we so choose that directional axis. No movement, again, it means our position at 3 seconds is a position of 1 meter, and our position at 5 seconds is a position of 1 meter. We did not move at all for those 2 seconds that elapsed. And then we're going backwards because we have a negative slope, right? If I were to track this kind of on a number line, I was at the position of 5 over here at 5 seconds, just like, or sorry, I was at the position of 1 at a time of 5 seconds. And then later, 2 seconds later, I'm at a position of 0.5. So I actually moved backwards from a position of 1.0 to a position of 0.5. Well, how did I get from here to here? I had to go backwards. And so a negative slope on a position time graph indicates negative velocity. So to summarize, here our v is equal to 0 because the slope's 0. Here our v is positive, and here our v is negative. The position time graph tells you about the direction of your velocity, or if you have any at all. But the other interesting thing is that the position time graph tells you about if you are accelerating or not. Let's think about what this means. If speed is a slope, or the slope tells us about velocity, what does that mean about if the graph is doing a curving trend? I'll draw a bigger curve here to illustrate the point. If I have a curve like this, if you take something called the tangent line, it's a term from calculus, it's like, or derivative, it goes crazy. Just suffice it to say, if I put a dot right here, I call it the pencil test. If I were to place a pencil on that dot so that it met that part of the line, wouldn't it kind of be like this? It would be a straight line. Well, that's called a tangent line. Now, what if I said I put my pencil over here? What would that line now look like? It would look like this. And that second line is what? Steeper. Oh, and steeper means faster. And if we're getting faster, our velocity is changing, that means we are experiencing acceleration. And so this would show, if this were a position time graph, this would show us speeding up. Why? Because we are increasing our slope of a position time graph, which means we're increasing our velocity. So a straight line on a position time graph means you have constant velocity, either positive, negative, or 0. And if it's a curvy line, it means we are experiencing acceleration. All right, so that's the overview for position time graphs. Now, let's go ahead and do a quick recap. What would these mean? All right, after I do each one, hit pause, think about it, and then unpause and see what it is. Graph A, what is that showing? Are you moving constant at all, forwards, or backwards? Pause the video. We are moving constant because it's a straight line, and we are moving with positive velocity because we have a positive slope. Graph B, what are you doing? Pause the video. Did you choose your answer? We are going at a constant speed backwards. Why? Because we have a negative velocity because the slope's negative. What is graph C showing? Pause and guess. Graph C is showing that we're not going very fast because it's not very steep, but then it gets steeper and steeper and steeper in the positive direction. What does that mean? That means that we are increasing speed, we are increasing our velocity in the positive direction, in the positive velocity direction. All right. So in this case, we would call that positive acceleration. Why? How do we know that? Because positive velocity getting more positive means that there's positive acceleration. Graph D is pretty tricky. See if you can get that one. Pause and guess. What's graph D doing? 0 slope, not moving at all. Kind of negative slope. Oh, moving kind of backwards. More negative slope, moving faster backwards. More negative slope, moving faster backwards. What does this mean? It means we started not moving at all, so we kind of started right here, and then we started moving backwards and backwards and backwards even faster. Remember Hansel and Gretel, right? The breadcrumbs? This means that we started at rest and we sped up backwards. All right, so that's why we don't use the term deceleration, because you'd get very confused at this point. It's less confusing to say we experience negative acceleration or we increase our negative velocity as we go. All right, same thing's happening with graph E. Graph F, did you guess yet? Graph F shows that you are at rest. Okay, this one you're moving forwards and then all of a sudden you go backwards, and this one is really fun. All right, let's think about this one. Pause for a second. Picture this. Okay, what's happening to this one? Really fast, slow down, stop, negative, more negative, more negative. What does that mean? That means we're hauling, we stopped and we took a break, and then we turned around and we started gaining speed in the opposite direction. So graph H is pretty fun. All right, let's look at velocity time graphs. These have different properties, and a lot of times you just have to read the graph. Okay, so let's take a look. Anytime you see this little red bar here, anytime you have a positive value on your velocity time graph, you are moving forwards. So that means that here you're moving forwards, and here you're moving forwards, and here you're moving forwards. This is the big place people trip up. They're like, but that is a slope of 0, Mr. Simpkins. But we're now looking at velocity time graphs. Yes, the slope is 0, but what is the value of velocity for this entire time? The value is 5. So a horizontal line on a velocity graph means that you're moving at a steady rate. What's happening to your velocity here? Well, now it's less than 5 and even less than 5, and it gets all the way to 0. So what just happened for that part of the graph? You were going fast and you started slowing down. But here's what really throws people for a loop. What happens from here over to here? Well, check it out. What is your velocity here? 0. And what is it here? -5. How do you get from 0 to -5? Answer, you're at rest and you're speeding up backwards. So a lot of people will say, well, Mr. Simpkins, the graph's going down. Going down means slowing down. No, it doesn't. What we can look at here for velocity time graphs is the rule is the further you are from the x-axis, the faster you're going. So see how far I am? I'm 5 units from the x-axis. That means I'm going a speed of 5. I'm going fast, right? I'm going backwards, right? But this would indicate speeding up backwards over here. All right, so that's just the tricky part that a lot of people deal with. Now, we defined acceleration in one of our previous lessons as the change in velocity over time. And we know from math class that slope is rise over run. Wait a minute. So if slope is rise over run, and I take the rise over run of a VT graph, I get acceleration. Boom, there it is again. And so that means for a velocity time graph, if I were to take the slope, I would get the value for acceleration. So here, a positive slope of a velocity time graph would indicate positive acceleration. 0 slope would be 0 acceleration. And negative slope would be negative acceleration. Let's look at this velocity time graph. Here we show a constant positive value, so we're moving forward constantly. Then we are slowing down until, actually we're at rest at this point, are we? We're at rest because what is the value for velocity at that point? It's 0. What does that mean? You're at rest. We speed up backwards, and then we have a steady backwards speed. So there's another quick example for you. Now, the thing about this class is the acceleration graphs will always be boring. They'll always be horizontal chunks. Sometimes they jump. Sometimes it jumps from one value to the next. But we use uniform acceleration in AP Physics 1 because we don't have the math tools at our disposal to deal with anything else. So your acceleration graphs always look super boring. So let me show you an example of how all 3 graphs might come together here with one that you haven't seen before. All right, let's look at this one just for some fun, and we'll wrap up our lesson today with this. Our cart rolls up the ramp and then back down. The origin is the middle of the ramp, so they want x equals 0 to be here, and up is positive, and that means that this way is positive. Let's go ahead and unpack this. All right, so that means we start at a position of negative x over here, and we go up to a position of some positive x. So we're going to begin our graph in a negative position. Now, once we reach the middle of the ramp, that's going to be a position of x equals 0. But it says we go up the ramp, and then we come back down. So what this is going to look like, I'm going to ignore that point here, because what we're going to do is we're going to go up the ramp, and we're going to get to the top, and then we're going to come back down. All right? Now, how does this play? Fast up, slowing down, slowing down, slowing down. Why? Oh, because we're going up a hill, right? And then you get to the top of the hill. That's at rest. That's when you're at the top of the hill. And then you speed up, speed up, speed up, speed up until you reach your initial position. How would that look on a velocity time graph? Well, it looks like we have some initial large positive velocity because we're moving up the ramp. Halfway through our trip, we're going to have 0 velocity. Why? Because you go to the top, you stop, and you turn around and come back down. And then we're going to return to the bottom of the ramp with an equivalent amount, but in the opposite direction of velocity there. So what I'm doing right now is translating from one to the next. Finally, we have a steady negative acceleration. Why? Because the slope of this VT graph is negative the whole time. A lot to throw at you. Check out the Canvas modules and some Khan Academy for a little extra review. But until next time, it's Mr. Simpkins in the Simpkins Physics Corner.